Okay, in this video I'm going to run through the density worksheet that's posted in Canvas. So this would be a great tool for you to work on the density sheet and watch this video at the same time, possibly. So I did one like this, number one, in the example, but we'll run through it again. So n of x is equal to the 250 times e to the negative 0.02x represents the number of trees per square mile in a coastal rainforest where x is the distance from the coast in miles. Assume the rainforest is rectangular and extends 40 miles inland and runs 120 miles along the coast. So that would look something like this, right? Or this would be 120, that would be 40, and we could do ocean here, let's say, and it's getting less dense as you run that way. So once again, we don't think about how do we divide this up, where we get to take a strip of forest that has roughly the same density, and then we find a formula for that, and then we integrate it so it would add up all of the little strips. So my integral is going to go from 0 to 40 because the change is a little change in x, and the area of that strip is 40 by 120. I mean 40 by I'm sorry, 120 by dx. So that would be 120 dx. That's my area of that strip. And then we got to multiply that by the density, because this is the number of trees per square mile. So the area would give me square miles, so we multiply that by 250 e to the negative 0.02x. And that would be what? 120 times 250, which is 3,000. So this is going to be 30,000, whoops, times, and if we integrate that, we get e to the negative 0.02x divided by negative 0.02. And we're going to evaluate that from 0 to 40. And if we plug that into, or if we use fundamental theorem calculus part 2, we find out that we get, let's see, we get 826,006.55. That means there is what? 826,006 trees. So that would be, we don't need the 0.55, so that would be 826,006 trees. Now the second part says find the average number of trees per square mile. Well, that's pretty easy. We just take the total trees, 826,006, and divide that by the square mileage, which is what? 40 times 120. That's 4,800. So then we take, that's a 6 right there. We take 826,006 divided by 4,800, and we get roughly 172 trees per square mile. Okay? Okay, so number 2 says oil spilling from the oil tanker is shown. It's a nice square oil tanker. The density of the oil at a distance x meters from the source is P of x equals that little guy there. Find the total mass of the oil if the outer edge is 10 meters from the source. So that means we have a radius of 10 meters there. Okay, so once again, we're looking for strips that are roughly the same density, because it looks like as you get further from the tanker, the thickness of oil is getting less thick, which makes sense because it's further from the source. So what would that look like? Well, I think if we take some strips like this, or those would be examples of strips that are roughly the same density. So we're going to take, we have to find the area of those strips and multiply it by the density equation. So we're going to integrate, and we're going to go e from negative 0.05x times the area of one of those strips. Well, the thickness of those strips is just a little change in radius, so we put a little dr out here. Well, the density of oil is at a distance x meters. So actually x is the radius, so we'll just call that dx then. That'll work because that x is also the radius. And then the length of that little strip, it's really kind of like a rectangle if we stretch it out. For our purposes, that's my little dx, or my little change in radius, and then this would be 2 times the radius times pi, wouldn't it? Because that would be the circumference of the circle. Oh, but it's not a full circle, it's a half circle, so it'd be 2 pi r divided by 2. So it'd just be x times pi. So we'll put a little x times pi in here. And so if we pull the pi out front, and let's see, we want to integrate from 0 to 10. And that would be x times e, x times, hey, why are you doing that? X times e to the negative 0.05x dx. So we need to integrate that from 0 to 10. So again, you can do that using the fundamental theorem of calculus part 2. And if we get, let's see, 113.35. So what does that mean? We took the number of the density of oil and multiplied by the square meters. So we're left with kilograms. So that'd be 113.35 kilograms. Total mass of oil. So total mass of oil is 113.35 kilograms. Okay. Consider the triangular region bounded by the x-axis. So we got a triangular region, x-axis, y-axis, and the line y equals 2 minus x. So that'd be 1, 2, and then we go like that. If the density is well, interesting. The density is the same as the equation. So the density is based on how far you are from the x-axis. So as you move, I'm sorry, how far you are from the y-axis, because it's based on x. So when x is 0, for example, the density is 2. When x is 1, the density is 1. When x is 2, the density is 0. So that's interesting. So we need to figure out strips that are the same density once again. So it looks like it's based on x, so my strip should go vertical like this, because that strip would have the same density. All that would have the same density. Okay, so we're going to integrate that. So the little change is in x, so that's going to be dx out here. So that means we'll integrate from 0 to 2, because this ends at 2 right there. Then I'm going to have 2 minus x as my density function, right? And then I got to multiply that by the area of that little strip. Well, the area of that strip is this distance times dx. Well, that distance is changing based on that line, so that'll bring in another 2 minus x in there. So this 2 minus x is brought on because of the density function. That 2 minus x is brought on by the height of the declining rectangle. Okay, so that means we're going to integrate from 0 to 2 of 2 minus x squared dx, which would be what? 2 minus x to the cubed, and we'd have to put a negative 1/3 out here because that chain rule is going to kick out a negative 1. We're going to integrate that from 0 to 2. So that would be what? Negative 1/3. Negative 1/3 times, if I put a 2 in there, that'd be 0. So I don't really need that. If I put a 0 in there, that would be 2 to the 3rd, which would be 8. I guess I should do it like this. 1/3 times 0 minus 8. So that would end up being 8/3. So the total mass is 8/3, and they didn't tell us any units, I guess. So 8/3. Yeah, we don't know what the units are, so we can't do that. Okay. Number 4, a rod of length 3 meters has a density described by 3 plus 4x grams per meter. So notice this is just based on the linear distance. So we got some kind of a rod that looks like this, and apparently it's getting more dense as you, or heavier, you could say, or as you go along the rod. Where x is the distance from the left end of the rod. So from here on, so this is lighter over here, it's going to get more dense or heavier. Okay, and the rod is 3 meters total. So we want to figure out, so this thing is basically going to be the same, you know, we want to, like for example, we have these little slices, and we need to, but we just need to multiply it by the total length of that little slice. Well, the length of that little slice is just going to be some small little change in x, so we'll call that dx. So this thing is just going to be the integral of 3 plus 4x times some little change in x. Because this is density, this is grams per meter, so we need to multiply the grams times some length. And each one of these little slices is just a wee little bit of length. And we're going to integrate from 0 to 3. So that would be what? 3x plus 2x squared divided from 0 to 3. And that would be 9 plus 18 minus 0, which would be 27. And this is, that would be 27 grams, wouldn't it? Okay, last but certainly not least, we have a grain silo. Grain silo is in the shape of a cylinder. It has a radius of 5 meters. That's cool. Okay, my kids keep coming through the back door and slamming it, so sorry about that. So the radius is 5 meters, and the silo is 20 meters tall. It is filled with wheat, and the density of the wheat, so the density of the wheat is 82, I guess I don't need to rewrite it, it's right there, 82 minus 0.3h kilograms per meters cubed. So that's like weight per volume. So it's definitely heavier as you get down in the bottom, because it's just packed down more dense because of the weight of the wheat above it. So again, we're looking for strips that are roughly the same density, and the density is based on the height, which would be the depth, you know, how far from the bottom. So that means we're going to have this little circular thing, right? So we'd say that that little disk has roughly the same density. So we're going to, our integral is going to be the density function times the volume of one of these little disks. And one of these little disks would be, the volume of that thing would be pi r squared times height, right? My height is going to be a little change in x, or a little change in h, I guess, in this case. And the radius is going to be 25, or the radius is going to be 5, so the radius squared would be 25. So that would be 25 pi. And we want to integrate from 0 to 20. 0 at the bottom, 20 at the top. So that'd be integral from 0 to 20. We could take the 25 pi out front, And we're left with, actually, let's just go ahead and integrate it right now. So we'll put still put the 25 pi out front. And that's going to be 82h minus 0.3h squared. So that would be 0.15. So they're going to multiply by 2. It'll make it 0.3. Okay? And we're evaluating from 0 to 20. So that'd be 25 pi times 82 times 20 would be 1640 minus 400, because that's 20 squared, times 0.15. So that'd be minus 60, minus, put a 0 in there, it'd be 0, put a 0 in there, it'd be 0, so it would just be that. So we got 25 pi times 160 minus 1640 minus 60. So 1640 minus 60, of course, is 1580 times 25 pi. And we get let's see, we get 124,092.9, and that would be kilograms. That would be the total kilograms of the total weight of the grain in the silo. Okay, so there's some fun density problems that we can use integration to find some total value, total weight, or total trees, or total something. So